When we stand under the open sky at night and look at the vast expanse of the universe, only one question arises in our mind. What is the existence of our Earth in this space spread over billions of kilometers? Because in this vast universe, our Earth is smaller than a grain of sand. Determining the size of our universe is challenging because it is expanding at a rate of approximately 300,000 kilometers per second. We live under an open roof of the universe, inside which there are billions of galaxies. And within each galaxy, there are millions of solar systems just like ours. In trying to understand this vast space, we are not able to fully understand even our galaxy. Nevertheless, scientists have attempted to observe this universe using powerful telescopes and have created maps of the universe spanning billions of kilometers. Today, we set out on a journey into the universe based on scientific data, exploring the edge of the universe billions of kilometers away. We are embarking on a cosmic journey, an extraordinary journey to explore the most remote corners of the universe. We will move beyond the galaxy and venture to the outer edges of the universe. Join us on this special episode of Cosmic Discovery as we journey to the final frontier of the universe. Observable universe. When we begin our journey to explore the universe, we must know what our final destination is. Is there a limit to the universe beyond which it ceases to exist? When we talk about the universe, we can only observe the part that is observable. The observable universe is a spherical sphere whose radius is defined by the distance traveled by light since the beginning of time. This region can be observed through Earth-based or space-based telescopes and exploratory probes. This is the part of the universe from where light has reached us. And it may surprise you to know that light travels a distance of 300,000 kilometers in 1 second. This speed may seem excessive to us sitting on Earth, but from the perspective of the universe, it is practical. For example, consider a galaxy that is 10 million, 100 million, light years away from our Earth. When scientists observe this galaxy using telescopes on Earth, they are essentially seeing the galaxy as it appeared 10 million years ago, because that's how long it took for light to reach us. NASA has compiled an image of a portion of the universe, and this observable region is often referred to as the observable universe. Telescopes, radio telescopes, radar, and space telescopes from around the world were used to create this image. The lateral length of the observable universe is approximately 93 billion light years. In simple words, it extends up to 9,300 crore light years. Scientists have seen approximately 4,650 crore light years of this vast expanse. So when we explore the edges of the universe, we are essentially looking back in time, attempting to understand the universe as it was billions of years ago. In the observable universe, the only galaxies whose light has taken less than 13.8 billion years to reach Earth are those galaxies, the estimated age of the universe. So, in a way, when we explore the boundaries of the universe, we are trying to go back to where the universe originated, and these modern telescopes are nothing less than a time machine for us. The James Webb Space Telescope and the Hubble Space Telescope have made significant contributions to observing the universe. Their keen eyes roam the cosmos all the time, providing us with a vivid glimpse of how the universe was billions of years ago. The GNZ11 galaxy is the farthest galaxy discovered to date, located 13.4 billion light-years away. A star in this galaxy exploded, and its light traveled for 13 billion years, reaching Earth in 2009. Astronomers believe that this galaxy formed after the Big Bang. In this vast cosmos, the Milky Way, the Sun, and Earth hold no special significance. They are merely a drop in the serene cosmic ocean. If our Sun were to vanish today, it would make no difference to the infinite cosmos, leaving only a faint glow meandering through the boundless universe. Our sun is just a pale speck for beings on other worlds. And during this 13.8 billion year life cycle, the universe has been expanding in volume, and we can see evidence of this phenomenon. Out of solar system. Now let's begin our journey from Earth. In this vast cosmos, the Milky Way, the Sun, and Earth hold no significance. They are merely equivalent to a drop in the tranquil Pacific Ocean. If our sun were to disappear today, it would make no difference to this infinite universe, leaving only a faint glow to wander through the boundless cosmos. Our sun is nothing more than a pale dot for beings on other worlds. At night, all the stars we see are stars from one small page of our Milky Way galaxy. We live here in our own galaxy, and during the night, we only see the stars from this small corner. Now, we take our journey beyond the solar system because staying within the solar system doesn't allow us to comprehend the vastness of the universe. Even after the last celestial body in the solar system, Neptune, our solar system, doesn't come to an end. Following this, a massive enclosure called the Kuiper Belt comes into play. Pluto, which was ousted from the list of planets, is also a member of this Kuiper Belt. Inside the Kuiper Belt, there are objects even larger than the asteroid belt, and some of them have their own moons due to their gravitational influence. After that, we move beyond the solar system and enter the interstellar space. Here, as we venture further into this region, we encounter the Voyager 1 spacecraft. It is approximately 24.4 billion kilometers away from Earth, making it the only spacecraft created by humans that has reached such a vast distance. Voyager 1 has unveiled some of the mysteries of the universe and is still functioning, although its battery has considerably weakened. It is traveling 20 times faster than a bullet fired from a gun. After advancing our journey, we have come so far from the boundaries of our solar system that our sun appears like an ordinary star from here. However, even from this distance, its gravity can be felt because countless comets can be observed here, bound by the gravity of the sun. These comets contain so much water that if gathered together, they could fill a planet larger than Earth with deep oceans. Scientists believe that most of the water on Earth has come from these comets. In these small icy rocks floating in space, life in the form of bacteria could exist in a microscopic form. A massive cloud of comets surrounds our solar system, known as the Oort cloud. It is said that the Oort cloud marks the outermost boundary of our solar system's gravity. Beyond this, the sun's gravity begins to weaken, resulting in much less gravitational pull. Now, the journey from here will take us into the unknown and mysterious space, where darkness is so profound that we won't be able to see anything even with our eyes. Here, we will need infrared vision to see. We have come so far from our Earth, but in the context of the cosmos, this is just a modest step for us. From here, we can see billions of stars all around, but now we are moving towards the nearest star cluster. This is our neighboring star cluster. This star cluster is 4.3 light-years away from our Earth. Its name is Alpha Centauri. In this star cluster, there is a group of 3 stars, where Alpha Centauri A and Alpha Centauri B are binary star systems orbiting each other. In this star cluster, there is also Proxima Centauri, a planet named Proxima Centauri b, which is present in the habitable zone just like Earth, and there is a possibility of alien life on this planet. But until we venture beyond the boundaries of the Milky Way galaxy, the true vast scale of the universe remains unclear. So let's continue our journey and move beyond the Milky Way galaxy. This is our Milky Way galaxy, home to billions of stars, including our own sun. The galaxy is so enormous that if light were to travel from one edge to the other, it would take approximately 105,700 years. However, compared to the massive galaxies present in the cosmos, our galaxy is relatively small. In the universe, there are galaxies much larger than the Milky Way, surpassing it in size several times over, the local group. So let's leave behind our solar system and galaxy as we enter intergalactic space. Venturing into intergalactic space, we see billions of galaxies stretching far into the distance. But all these galaxies are part of different galaxy groups, And here is our galaxy cluster, where our Milky Way galaxy and other neighboring galaxies coexist. This small group of galaxies is called the local group. This local group of galaxies extends across 10 million light-years. The largest galaxy in the local group is the Andromeda Galaxy, which contains approximately 10 trillion stars. In our Milky Way galaxy, there are about 200 billion stars. Our Milky Way galaxy is the second largest member of a small part of this local group. The local group contains more than 30 galaxies and hundreds of smaller satellite galaxies. However, there are 4 major galaxies that are in relatively close proximity within the local group. In fact, the 3 largest members of the group are thought to be on a collision course as they are pulled together by gravitational forces to gain control over the tenuous expanse of the universe. The term local group was introduced by Edwin Hubble in Chapter 6 of his 1936 book, The Realm of the Nebula. There he described it as a special small group of nebulae that are isolated in the general field and characterized it by decreasing brightness, identifying its members as M31, Andromeda Galaxy, the Milky Way, M33, Triangulum Galaxy, denoted as the Large Magellanic Cloud and the Small Magellanic Cloud. Laniakea Supercluster. Now, as we continue our journey and move beyond the local group, we start to see many groups of galaxies, each containing galaxies just like our local group. These groups of galaxies, when combined, form a very large supercluster. Arriving here, even the local group that contains our galaxies starts to look small. What we see on our screen right now is the Virgo supercluster. Within this Virgo supercluster, our local group of galaxies also exists, and our local group appears to be just a small patch within it. We have moved so far from our home that forget about seeing our sun from here, even our galaxy is not visible. Our local cluster now looks like a small patch in this huge Virgo supercluster. Look how huge the Virgo supercluster is. It contains more than 100 local groups of galaxies. The Virgo supercluster spans a distance of 110 million light-years. But friends, this Virgo supercluster is also a part of a much bigger supercluster. As we move further on our journey from the Virgo supercluster, we encounter many more superclusters. Like the Virgo supercluster, there are several such superclusters that together form the Laniakea supercluster. Within this, the Virgo supercluster appears much smaller. And here is our Virgo supercluster, appearing like a small patch. In this vast expanse, our galaxy's local group is not even visible as a dot. The Laniakea supercluster extends over 520 million light-years, containing more than 100,000 galaxies. It sprawls through space, covering over 500 million light-years. The most massive galaxy clusters within the Laniakea supercluster include Virgo, Hydra, Centaurus, Abell 3565, Abell 3574, Abell 3521, Phoenix, Eridanus, and Norma. Approximately 300 to 500 known galaxy groups and clusters are part of the entire supercluster, and the actual number could be much larger as some are traversing regions obscured by the zone of avoidance, an area in the sky obscured by Milky Way gas and dust, making them inherently less known. Superclusters are some of the largest structures in the universe, and defining their boundaries, especially from within, can be challenging. Within a given supercluster, most galaxy motions are directed toward the center of mass, where the gravitational pull is concentrated. In the case of Laniakea, this gravitational focal point is referred to as the Great Attractor, influencing the motion of local galaxy groups, including the Milky Way galaxy within our local group and all others throughout the entire supercluster. In contrast to its component groups, Laniakea is not bound by gravitational attraction and is thought to be separated by dark energy. While the existence of the Laniakea supercluster was confirmed in 2014, studies in the early 1980s had already suggested the possibility of several superclusters being connected at that time. Nearby superclusters to the Laniakea supercluster include the Shapley supercluster, Hercules supercluster, Coma supercluster, and Perseus Pisces supercluster. At the time of defining Laniakea, The boundaries of superclusters and those on the outskirts were not clearly known. Since then, there has been significant improvement in the study of the edges and structures beyond superclusters. And beyond the boundaries of the Laniakea supercluster, situated more than 650 million light-years away from Earth, we encounter the Shapley supercluster, a remarkably packed, vast supercluster unity in space, where thousands of gravitationally bound, densely clustered galaxies reside. Moving a bit further, beyond 870 million light-years from Earth, we find the Vela supercluster. It is now understood that these two significantly important galaxy superclusters, from a distance, exert a subtle influence on Laniakea's galaxy clusters. This impact is particularly noticeable in enhancing the capacity of the Norma cluster, revealing the profound gravitational pull of the Great Attractor. Sloan Great Wall. As previously mentioned, the Laniakea supercluster lacks gravitational binding, distinguishing it from the Shapley concentration and the galaxies within the Virgo supercluster. Consequently, categorizing these higher-order aggregations as structures remains challenging. However, cosmic propagations within the vast cosmic web can extend beyond superclusters, giving rise to structures known as galaxy filaments. These filaments represent the largest cosmic formations, appearing as chains of galaxy superclusters, assuming thread-like configurations across distances exceeding 250 million light-years, with some even larger. Venturing 1 billion light-years from Earth, we encounter the Sloan Great Wall, an immensely colossal filament-like structure identified through data from the Sloan Digital Sky Survey. This structure forms a massive arcing arrangement of galaxies within a densely populated region of space. It encompasses numerous densely packed galaxy superclusters, with the largest, SCI 126, situated near its center. The complete structure spans over 1.3 billion light-years in its maximum extension. However, subsequent discussions have suggested that this immense scale might result from the alignment of 3 galaxy superclusters and filaments rather than a single unbroken chain. Nevertheless, upon its discovery in 2003, the Sloan Great Wall swiftly earned the title of the largest known cosmic structure, maintaining this status for approximately a decade. Active galactic nuclei. As we journey beyond the Sloan Great Wall, approximately 1.38 billion light-years away from Earth, our perspective shifts. At this juncture, our light signals encounter delays surpassing 1.5 billion years. And so, from this distance, we start to see objects more characteristic of the younger universe. Billions of years in the past, galaxies like the Milky Way and M31 underwent significant evolutionary transformations, engaging in cosmic collisions with neighboring galaxies, merging their stars and gases. These cosmic mergers inundated the galactic cores with rich reserves of gas conducive to star formation, fueled by the dynamic tidal forces resulting from the mergers. When a substantial amount of gas accumulates around a galaxy's central region, especially surrounding its black hole nucleus, a myriad of intriguing electromagnetic phenomena can unfold. When the central black hole of a galaxy interacts with the surrounding gas, we refer to it as an active galactic nucleus, AGN. This interaction invariably results in the release of an immense amount of radiant energy, enhancing the galaxy's brightness across various electromagnetic wavelengths, such as in the radio spectrum. Radio galaxies represent a specific category of AGNs and are consistently found in elliptical galaxies like Messier 87. As the gas encircling the nucleus of this galaxy gets ionized, subatomic particles become captured within the magnetic field of the black hole and are directed towards its polar axis. These particles are then expelled away from the event horizon at velocities close to the speed of light through a pair of relativistic jets, carrying the material over thousands of light-years into space. The ejected material emits a glow of radio-loud synchrotron radiation, and on occasion, these emissions can extend to much larger scales than the galaxies that host them. As we explore the cosmos, we discover that radio galaxies become more noticeable at higher redshifts compared to the gradually diminishing optical emissions of radio-quiet galaxies. There's 3C327, one of numerous identified radio galaxies. Moving approximately 1.5 billion light-years further, we encounter Alcyoneus, currently recognized as the largest radio galaxy, with emissions stretching an impressive 16 million light-years. However, positioned between these celestial bodies lies 3C273. Yet, 3C273 is not just a radio galaxy. It is a quasar, distinguished as the brightest and most energetically active type of active galactic nucleus. Quasars. Recently, scientists have discovered the brightest object in the universe, which, even if combined with 140 trillion suns, would still outshine them. Quasars are the most luminous known objects in the observable universe. They are about 100 times more luminous than our entire Milky Way galaxy, containing approximately 400 billion stars. They are so bright that wherever they exist in the cosmos, they illuminate their host galaxies with their brilliance. They also emit radio waves, X-rays, and light waves. Quasars hold the record for the most distant objects observed so far. The quasar named Euelas J, 1120 plus 0641, the farthest known quasar, is located approximately 29 billion light-years away from us. Quasars can be identified solely using radio telescopes. With a regular optical telescope, a quasar would appear like an ordinary bright star. Even the Hubble Space Telescope finds it challenging to distinguish between a quasar and a star. The distance between a quasar and a star is difficult to discern. While a typical star might be around 100 light-years away, a quasar could be millions or billions of light-years distant. The first quasar was discovered in 1950 and was named 3C273. Since then, approximately 200,000 quasars have been identified. Due to the immense distances from Earth to quasars, they are considered some of the oldest known objects to us. They provide insight into the early years of our universe. It is believed that a quasar is a compact region found in the central part of a massive galaxy, and it surrounds a supermassive black hole situated at the center of the galaxy. A supermassive black hole has a mass equivalent to 1 billion solar masses. This means that the black hole is as heavy as 100 million stars. The accretion disk is a disc-shaped structure, typically composed of gases, that orbits the black hole. However, this material rotates at extremely high speeds around the entire perimeter of the black hole. Quasars eventually die out. This occurs when a supermassive black hole consumes all the material in its accretion disk, and there is nothing left to feed upon. It has been found that quasars are moving away from us at speeds of at least 93,200 miles per second, which is half the speed of light. Some quasars travel at 93% of the speed of light. By combining the redshift of quasars with Hubble's law, scientists have discovered that quasars are the farthest objects visible to us in both time and space. The nearest known quasar, known as IC 2497, is located 730 million light-years away from us. It is believed that our Milky Way might have hosted a quasar as a guest once, but it has now died. When our galaxy collides with the Andromeda Galaxy in about 5 billion years, a quasar may emerge in our galaxy. However, to observe a significant number of quasars, we need to explore much deeper into space. In the deep universe, approximately 8.4 billion light-years away from Earth, we encounter quasar groups, a time when the universe was much younger and smaller, less than half its current age. At this distance, quasars become visible at significantly higher frequencies. As we approach 9 billion light-years from Earth, we begin to witness quasar galaxies in quantities and formations that resemble vast cosmic structures, such as the Sloan Great Wall. When we look 8.8 billion light-years from Earth, we come across the first of 3 extraordinary quasar groups, U1, 11. This group consists of 38 quasars spread over a distance of 2.2 billion light-years, marking the largest extension. Adjacent to U1, 11 but slightly farther away, lies the closed Campusano LQG, another cluster of 34 quasars. This cluster also appears to cover a distance exceeding 2 billion light-years. Finally, at approximately the same distance, we find the most extensive grouping of all, the huge LQG, featuring an assortment of 73 quasars spread across an expanse greater than 4 billion light-years. It's important to note that these assortments are unlikely to be actual structures and are more likely the result of random alignments within which certain patterns emerge. Farthest galaxies. This is the galaxy GNZ 11, located in the Ursa Major constellation. GNZ 11 is a highly redshifted galaxy, meaning it has an extremely large redshift. What's special about this galaxy is that it is the farthest galaxy discovered so far. The image we are seeing of GNZ 11 is 13.4 billion years old, which means it captures an image from about 40 million years after the Big Bang. Due to this, the typical distance of this galaxy is estimated to be 13.4 billion light-years. The discovery of this galaxy was based on observations from the Hubble Space Telescope and the Spitzer Space Telescope. Scientists calculated the distance by measuring the redshift of the galaxy using the Wide Field Camera 3 of the Hubble telescope. This redshift occurs due to the expansion of the universe. In comparison to our Milky Way galaxy, GNZ 11 is 5 times smaller, and its mass is only 1% of the Milky Way. However, the formation of stars in GNZ 11 occurred 24 times faster. Previously, the galaxy EGSY 8P7 was considered the most ancient, but GNZ 11 is now recognized as 150 million years older. GNZ 11 held the title of the farthest detected galaxy only until as recently as 2022, when astronomers at the University of Tokyo managed to bring an even more remote, and thus earlier galaxy into view. This galaxy, termed HD1, it formed a mere 330 million years after the birth of the universe, and well within 100 million years of the first stars, the last edge of the universe. Let's continue our journey, and as we move beyond all the superclusters, it feels like the universe is resembling our human brain. The structures of the universe seem to be like the sensory organs of our brain. Is there really a connection between the universe and the human mind? Coming to think of it, my head is spinning. Anyway, let's move forward in our journey to the observable universe, where our Laniakea supercluster appears like a small dot. As I mentioned earlier, this is the observable universe, meaning the known universe so far. Everything we know about the universe is contained within it. The observable universe is a spherical region with a diameter that can be observed using Earth-based telescopes and space-based observatories. It includes everything from the smallest particles to galaxies, seen through current technologies. Now the question arises, what lies beyond this circular sphere? Does our universe end here? Different people have different opinions on this. Some scientists believe that it's possible the universe could continue expanding indefinitely, reaching beyond what we currently observe. However, if light cannot reach us from beyond a certain point, then we cannot gain knowledge about what lies outside the observable universe. Scientists also speculate that there might be countless universes similar to ours, forming a multiverse. In these universes, our own universe could be like a tiny droplet in a vast ocean. Whether the existence of a multiverse is real or not, no one knows for sure. And as of now, scientists have found no evidence of the multiverse beyond the observable universe. However, it's certain that the observable universe cannot be the end. There must be something beyond it, something of which we have no knowledge. But what could that be? What lies beyond the observable boundary of the universe? Can future technology take us beyond the observable edge of the universe? Approximately 13.75 billion years ago, our universe came into existence. Soon after, primitive light began spreading throughout the entire universe, marking the beginning of the early universe. During this time, the universe was also expanding. After the initial explosion, the expansion of the universe slowed down, but since then, due to the effects of dark energy, the rate of expansion has been steadily increasing. Fundamentally, since its establishment, the universe has been continuously and rapidly expanding. Astrophysicists estimate that the oldest observable photons, those we can see, have traveled a distance of 47 billion light-years since the Big Bang. This implies that our observable universe is roughly 93 billion light-years wide. Within these approximately 93 billion light-years, everything from quarks, quasars, stars, planets, galaxies, nebulae, black holes, and everything else that is observable has been included, although only the light that has reached us in this time frame is accessible in the observable universe. What we can observe is just a fraction of the entire universe. If the universe is only 13.8 billion years old, how can its size be 93 billion light-years? There doesn't seem to be enough time for light to travel such vast distances, right? Ultimately, understanding this aspect of physics is the key to comprehending what lies beyond the observable edges of the universe and whether we can ever reach there. To break it down, according to the principle of special relativity, objects cannot move faster than the speed of light relative to each other when they are close. However, there is no such rule for objects that are extremely far apart, where the space between them is expanding. In essence, it's not that objects are traveling faster than the speed of light. Rather, the space between them is expanding, causing them to drift apart at remarkable speeds. Ultimately, this means that we can only reach the observable edges of the universe if we develop a method of transportation that either 1, allows us to travel faster than the speed of light, something most physicists consider impossible, or 2, transcends space-time using concepts like wormholes or warp drives, which are also deemed unlikely by most physicists. According to the principles of cosmic inflation, the size of the entire universe is at least 10 circumflex 23 times larger than the observable universe. There is so much more of the universe that we are missing out on. So, what are we really missing? What lies beyond the observable universe? Unfortunately, since we cannot see or measure it, we do not know what lies beyond the edge of the observable universe. However, there are several theories about what might exist in the vast unknown, facing the unknown. Despite its complexity, this is one of the easiest ideas to grasp. Astronomers believe that the space beyond the observable universe, which is distributed much like the observable universe we see around us, could be an infinite extension. This seems logically sound. After all, it doesn't necessarily mean that a region of the universe we observe around us is different from a portion of the universe beyond the observable universe. And to be honest, who can imagine a universe with an end, a massive brick wall hidden at its edge? So, in some sense, infinity here means that beyond the observable universe, you'll encounter not just more planets, stars, and other matter, but ultimately, every possible thing. Each possible thing. This means that if this is true and we take it to its logical conclusion, somewhere there is another person who is exactly like you in every possible way, and another you who is slightly different from you in every way. The possibilities are endless. One is an inch shorter. One got hit by a bus 5 years ago and died. One is missing a finger, etc. Another concept is related to something called dark flow. In 2008, astronomers made a bizarre and unexpected discovery. All galaxy clusters were flowing in the same direction at speeds exceeding 2 million miles per hour. One possible explanation: enormous structures outside the observable universe exerting gravitational influences. As far as the nature of these structures is concerned, they could be practically anything, marvelously vast accumulations of matter and energy on a scale we can hardly imagine, or even intricate cosmic filaments trapping gravitational forces from other universes in the space-time. We have no idea what these vast entities could be. However, recent analyses have claimed to debunk the dark flow model, but the controversy remains unresolved. Another option involves the idea of a universe within universes. Some people believe that our entire universe might exist within a small bubble amid a vast string of other bubbles. Theorists refer to this concept as multiverse. What's intriguing about this notion is that it suggests these universes could potentially come into contact with each other. Gravitational influences might flow between these parallel universes, and when they interact, it could lead to the occurrence of a Big Bang, creating our observable universe. Your final statement explores the possibility that our universe could be just one bubble among many in a vast cosmic cluster. Some scientific theories indeed consider the possibility of multiple universes, known as the multiverse. Each universe in the multiverse could have its own set of rules, galaxies, planets, and life. This concept is intriguing and aligns with various hypotheses in theoretical physics. The idea of a multiverse arises from theories like string theory, which suggests the existence of multiple dimensions and universes beyond our observable one. However, it's essential to note that the multiverse hypothesis is still speculative and lacks direct empirical evidence. In the quest to understand the nature of our existence and the cosmos, scientists continue to explore various theoretical frameworks, and the concept of a multiverse is one fascinating avenue in cosmology. The ideas we've discussed include topics like the multiverse, dark flows, and various theories about the nature of our universe, which are fascinating and hypothetical aspects of cosmology. Many of these concepts have emerged from cutting-edge research in theoretical physics, and they shed light on the ongoing quest to understand the mysteries of the universe. It is important to recognize that these ideas are theoretical and, in many cases, still lack empirical confirmation. Scientific investigation and exploration in these areas continues to expand our understanding of the universe and our place within it.